Welcome to this lecture about solar photovoltaics for the production of electricity. This is our last lecture on the production of electricity. In another lecture, we have already seen that it is possible to produce steam with solar heat and therefore to produce alternative current with a steam turbine. Photovoltaic is a completely different technology. Photovoltaics, often abbreviated to PV, is the conversion of light into electricity using materials called semiconductors and the photoelectric effect. There are semiconductors which contain mainly negative charges, electrons therefore. There are also called N semiconductors, N from negative. There are also semiconductors which contain essentially positive charges. We call them P semiconductors. When you bring them together, something happens at the junctions where negative and positive charges are attracted to each other, by which a kind of neutral and stable zone with as much negative as positive charges is built up, overlapping the junction. That is the white part on the picture. When solar radiation, which consists of photons, travels through the N semiconductor and hits the junction, the junction absorbs energy from the radiation, and this energy is just enough to help the electrons that are in the neutral zone at the P side to jump further into the P side. This, in turn, allows the electrons in the neutral part of the N side of the junction to jump to the P side to re-establish neutrality, which in turn gives the opportunity to the electrons above in the N semiconductor to move to the neutral zone. There is therefore a continuous flow of electrons from the N side to the P side, and if you put a conductive wire or strip between both sides, the electrons will take the shortest way through the wire and you get DC electricity, just like with fuel cells. The efficiency of PV cells is of course defined as being the electrical output divided by the incoming solar radiation. Just like for other renewables, we will consider the primary energy to be zero as well as the CO2 equivalent emissions. The actual efficiency of PV cells varies between 5 and 30%, 30% being really exceptional. However, there is research on PV cells with even higher efficiencies. This low efficiency comes, of course, from energy losses. To dislodge an electron from the P junction, a very specific quantity of energy is needed. If you give more than needed, this additional energy is just lost, as the electron cannot use it and just takes what it needs to jump. If you give less energy, all of it is lost, as the electron cannot use it to jump. So, at one side, the photons in the solar radiation have a much higher energy than the energy needed by the electrons to jump to the P side. This excess energy is lost as heat. That is around 30% of the incoming solar energy. At the other side of the spectrum, the photons from the infrared have too less energy to boost the electrons. Also, this energy is lost. That is around 23%. This determines a theoretical maximum efficiency, although there are developments to make more use of the whole spectrum by using several layers of conductors, each with a specific absorption spectrum, making the efficiency increase to almost 30%. In total, there are even more losses, as many of the photons are just lost in the material and do not hit an electron, and there are also losses in the electrical circuit and junctions. Currently, 90% of all PV cells are made from silicon. Monocrystalline cells, right on the picture, are a bit more expensive but have a higher efficiency than multicrystalline cells, left on the picture. There are also developments around plastic materials, so-called amorphous organic or polymer cells, which are more flexible. For the moment, their efficiency is at the lower end, with 5 to 11% efficiency. But how to size PV cells in practice? Well, producers deliver in general data about the nominal power of their PV cells. This is expressed in watt-peak, WP, a bit similar to the rated power in wind turbines. It is the maximum amount of DC electricity a panel will deliver under a standard solar irradiation and outdoor temperature. This includes, therefore, the efficiency of the cell. Combined with equivalent full load hours from the location, this allows for a rapid estimation of the total annual electricity yield. However, such estimations of the full load hours may be difficult to find. Sometimes they are given by the producer, sometimes energy agencies or research institutes may have data. For example, as a rule of thumb, the number of full load hours in the Netherlands is around 900, while in Mumbai it is around 2300. If we take the example of 1 square meter of panel with a peak power of 160 watt peak, this leads to a production of 144 kilowatt hour in the Netherlands and 268 in Mumbai. These are quite simple calculations for a quick sizing. The reality is, as usual, a bit more complex. In a lecture about solar heat, we have already addressed the problem of intermittency by noticing the need for heat storage, as solar radiation may be present when not needed and absent when needed. Exactly the same happens with the electricity production. Let's take a typical summer and winter week in the Netherlands with a typical electrical demand for lighting and appliance, estimated the same way as we did in the course energy demand in buildings. In this example, it was a large office building with a total floor area of almost 13,000 square meters and on average 10 watt per square meter electricity need, and for appliances and 8 watt per square meter for lighting. At night there are still servers, some computers and lighting on, so the electricity demand is not zero. You see this electrical demand in gray on the picture for a summer week. In orange, you see the electricity produced by 2,000 square meters of PV cells. The largest part was put on the roof and the missing square meters were put on the facade. So, you see here that sometimes the PV cells produce more than needed, that is the orange part that does not cover the gray one. Sometimes it produces a part of what is needed, that's the orange-gray part. And there are also many hours where there is only a gray part. This electrical demand is not covered at all. Two parameters are used to characterize this phenomenon, the OEM and the OEF. The OEM is the on-site energy matching and is the fraction of electricity produced by the PV cells that can be directly used in the building. In the graphic, it is the orange-gray domain divided by the sum of the orange and the orange-gray parts. When the OEM is 0, the mismatch is complete, and when OEM is 1, all energy delivered by the PV cells can be used directly. One could also say that 1 minus OEM gives the potential for electricity storage, or for selling the electricity to the grid. The OEF is the on-site energy fraction and is the fraction of the needed electricity that is covered by the PV cells. In the graphic, it is the orange and gray domain divided by the sum of the gray and orange-gray parts. When the OEF is 0, the mismatch is complete, and when OEF is 1, all electricity needed by the building is covered by the PV cells. One could also say that 1 minus OEF represents the electricity that must be brought from the grid or taken from a battery. In our example, the OEM is 0.87, meaning that 87% of the electricity produced that week was directly used in the building. The OEF is 0.54, meaning that this covered only 54% of the total demand. You see here now how this changes in a winter week. The OEM is 1 because the production by the PV cell is always less than what is needed, so everything is used. The OEF is very low. Only 3% of the electrical demand can be covered by the PV cells. This was for the Netherlands. But what happens in a more sunny and warm country? Let's take the same building, this time located in Mumbai. The building is exactly the same, but the cooling demand is very high there, so I added the electricity demand by the chillers to the electricity demand for appliances and lighting. That is why the grey area, representing the needed electricity, is much higher than in the Netherlands. We still have 2,000 square meters of PV cells, but the irradiation in Mumbai is much higher than in the Netherlands, so much more electricity is produced. In this case, we see that the OEM is 1 again, meaning that all electricity produced by the PV cells is used in the building, but this time 34% of the electricity needed is covered by the PV cell. Let's go back to our Dutch summer week. With 2,000 square meter PV cells, we had an OEM of 0.85 and an OEF of 0.54. If we double the amount of PV cell to 4,000 square meter, the OEF increases a bit to 67%, meaning that 67% of the demand can be covered by the PV cells. The OEM decreases a lot. Instead of 87% of the production being used in the building, only 55% can be used directly. Therefore, 45% could be stored in batteries used to make hydrogen or sold to the grid. Which brings us to some facts about electrical grids. We have seen that electricity produced by engines and turbines was alternative current, AC. That's one of the reasons why the electrical grid is AC, also home current is AC. But we have seen that PV cells and fuel cells produce DC current, as do batteries. So, to use this current in the electrical grid, it should be first converted to AC current. During this conversion, around 7 to 10% of the power is lost. Most home appliances, not all of them, but many of them, work in the basis on DC and are equipped with a converter that transforms AC to DC. This converter is placed in the product itself. Here too, there are around 7 to 10% losses. Using directly DC current into home appliances would therefore save energy around 14%. That is substantial, and that is why a lot of research is done in combining AC and DC networks. The idea is to use micro or mini DC grids at the level of groups of buildings and to use the AC networks for larger distribution, limiting this way the number of AC-DC and DC-AC conversions. We saw it earlier in the presentation. There are a lot of heat losses in such a PV cells, as more than 50% of the incoming solar radiation cannot be used to help the electron jumping through the NP barrier. This means that cogeneration is possible with PV cells, at least if they have been designed in such a way that this heat can be recovered. This is what happens in a PVT cell. Electricity is produced by the PV part, while a water pipe circulating on the back using the heat lost to heat the water. This warm water can be used for hot tap water and also for space heating. In that case, the warm water is the heat source of a heat pump. Alternatively, air can be circulated in the pipes and heated this way. Another advantage of this is that it also cools the PV cells, which then performs better. You see on the right, pictures of solar farms in which large fields of PV cells are used, PV, not PVT, for power generation. This is very promising, especially for locations with high irradiance, like in deserts, where huge power plants can be constructed this way. Such PV fields are also developed in less desertic areas. See picture below. The question here is how sustainable it is to use ground and therefore to compete with food production and ecological wellness to produce electricity. Better places could be found, like buildings and cities. Above left are most horizontal PV cells placed on a roof in two directions. The orientation of PV cells has become less important as modern PV cells have better capabilities to work with diffuse light. Even placing them in the north, on the northern hemisphere, therefore not facing the sun, is possible. Below left, you see an example of PV cells fully integrated in the roof and covering the complete roof. In the middle, an example of so-called semi-transparent PV cells on the roof of the railway station of Rotterdam. On these panels, only half of the surface is covered by PV cells, letting the light pass and producing shadow during the warm weather. The other half produces electricity. These semi-transparent PV cells can be used as cover for atria or vertically as solar blinds. The right picture shows an example of vertical panels used as coverage material for the CSI Tower in the UK. During this lecture, we discussed the working principle of PV cells and how to use rough data to size them. We also went into more details about the mismatch between demand and supply and learned the meaning of OEF and OEM. The need and possibilities for storage were shortly discussed, as well as smart grids and the losses during the conversion from AC to DC and conversely. PVT panels for cogeneration of heat and power were discussed, as well as integration of PV cell in buildings. Thank you for your attention.